Yeah, that was a little bit of Sweet George Brown. That was used as the Harlem Globetrotters theme song that you may be familiar with, an old ragtime song. So, welcome to Trigonometry, Section 2.1. We're going to be looking at unit circle and a lot of things that have to do with graphing today, just introducing that idea. So, to begin with, we're going to start talking a little bit about the unit circle and how that works out and everything. So the unit circle is basically just a special circle that has a radius of 1. To begin with, we're going to go through and just talk a little bit about definitions. So we know that the sine, we've already learned that the sine is y over r. We've learned that the cosine is x over r. The tangent is y over x. And then we know the reciprocals. We know the sine and cosecant are reciprocals, so that's r over y. The cosine and the secant are reciprocals, so that's r over x. And the cotangent is the reciprocal of the tangent, so that becomes x over y. All right, so in a unit circle, things change a little bit. So if it's true that the definition of the sine is y over r, then this becomes y over 1, with r being 1. So then that just becomes y. Okay, so that does simplify things a little bit. The sine is just going to be the y value on a unit circle. So the reciprocal of y over 1 is going to be 1 over y. So the cosecant in a unit circle is the reciprocal of the y coordinates. And then the cosine is going to be x over r, so r is 1. So that means the cosine now simplifies to just the x value. The secant is the reciprocal of x, so that's 1 over x. And then the tangent and cotangent don't simplify because they don't have the radius in it, so it's just y over x and x over y. So here's kind of what we're after here. This is the big crescendo here, is the cosine is the x value of an ordered pair on the unit circle, and the sine is the y value. Okay, so we're going to begin to look at a little bit of the unit circle. Okay, a couple of things that I also want to show you is in a unit circle, for example, the radius is 1, so I just want to use this as an example right here. I'm going to take and make a right triangle out of this, like this, and of course this would be the x value of that point. You know, you have some sort of an arbitrary point x and y, and then you have a y value like this. And then we would have this radius of this right triangle. Now, since we're talking about a unit circle, that's r equals 1. Well, we know from the Pythagorean theorem that a squared plus b squared is c squared, so we would get x squared plus y squared equals 1 squared, or just x squared plus y squared equals 1. So here's the point. In a unit circle, the x value is the cosine. So the cosine of this angle alpha in a unit circle is represented by the cosine. So this is going to become cosine of alpha squared. The y value in a unit circle, we just talked about, turns into being the y value, or the sine. So y gets replaced with sine alpha squared equals 1. So what we end up with then is cosine squared alpha, that's how we write the cosine of alpha squared, plus the sine squared of alpha is equal to 1. Now that's an identity that we've looked at before. That's where it comes from. Okay, so this unit circle we're going to learn about is I call it the god of trigonometry, because so much of trigonometry comes from this incredible circle. All right, so we're going to go on to the next page, and we're going to start beginning to look a little bit at the unit circle. So what I've done on this is I've drawn a picture of the unit circle. I'm going to zoom on this just a tad bit here, and then we'll kind of begin to look at this unit circle. So the idea on a unit circle is, since the radius is equal to 1, you have certain points on this unit circle, like you got this point 1, 0. That's just because the radius is 1, so this point's over 1. Then we have a point 0, 1. Okay, again, the radius is up 1, so that point's up 1. And then if you go this way, we have a point -1, 0. And finally, down at the end, the bottom, the tail end, we got 0, -1. Okay, now the question's going to be, where do all these other points come from? So notice they have fractional values in it, and they all kind of look very similar. They have square roots of 2, square roots of 3. So I'm going to show you where all those points come from in the unit circle. And then I've written down all of these radian values of the angles like this. Well, if you look at these angles, we have a 30-degree angle, a 45-degree angle, and a 60-degree angle. So this has something to do with the special triangles that we've learned, okay? All right, so we're going to do a little bit of a derivation on this. So these numbers, and I'm talking about the points on the unit circle, where they come from is they come from the special triangles that we have learned about. Okay, so I'm going to do a derivation of a 30-degree angle, then a 45-degree angle like that. So let me draw a basic coordinate system to begin with, and then we'll look at, kind of use this to derive the 30-degree angle like this. All right, so let's say on the unit circle now, let's make a 30-degree angle. This is not drawn to scale, but let's say that's a 30-degree angle right there. And let's make this into a right triangle. And what we would have is, of course, the x value, we would have the y value, and we would have the r value. So this is a 30-60 triangle that we've learned. And the sides went like this. The side opposite 30 was 1. The side opposite 60 was square root of 3. Now, what we had in this was 2. So we had that triangle I said that was easy as 1, 2, square root of 3. Well, here's how you come up with these points. So basically, if I was to go through, if I wanted this thing to become a unit circle, I don't want the radius to be 2, I want it to be 1. So I can divide every side of this special triangle by 2, and I get a unit circle. Okay, so that radius is now 1. This y value is now 1/2. And then this x value is now square root of 3 over 2. So it turns out if you have a triangle, if you divide all of the sides of a triangle by the same number, you're not going to change the angles. So what we end up getting is this point that would be on the unit circle, actually. If you kind of can imagine the circle going around that, you would have a point, x value square root of 3 over 2, y value 1/2. Okay? So that's where that point comes from. So I'm going to scroll up and just take a look at that point. That's the point that we just derived, is it square root of 3 over 2 and then 1/2 like that. Okay? Now the next thing I'd like to do is show you the derivation of the point on 45, which is very similar. So I'm going to draw out, again, a coordinate system. And this time we're going to look at a 45-degree angle. So I'm going to just sketch out an example of a 45-degree angle. That's kind of a crooked radius, but you get the point. So again, I could draw a triangle straight down to the x-axis, formulating a 45-45 right triangle. And that, of course, gives you this point right here that we're looking at is going to have an x value and a y value. So we're going to reason out what those things are. So what we learned was, in a 45-45 right triangle, we learned that the sides could be reduced to 1, 1, square root of 2. Now, in a unit circle, we don't want the radius to be square root of 2. We want it to be 1. So what I can do is I can divide everything in this triangle, each side of this triangle, by square root of 2. So what I would get then is, of course, this radius would become r equals 1. Okay, like this. Now this side right here is going to be 1 over square root of 2, so we could certainly rationalize that denominator the way we've learned how to do by multiplying by square root of 2 over square root of 2. So that's going to give square root of 2 over 2. So that y value on this unit circle is square root of 2 over 2. And by the same logic, if you have x is equal to 1 over square root of 2, by rationalizing that denominator, you're going to get root 2 over 2. So that's where this point comes from on the unit circle, as we have square root of 2 over 2, square root of 2 over 2. Points are the same because they come opposite equal angles. So what I just showed you is the derivation of this point, and I showed you the derivation of the 30-degree one. The 60-degree angle is very similar to the 30-degree angle. So that is where all these points on the unit circle come from. Really is from those 30-60 triangle and the 45-45 right triangle, like that. Okay, so going on to the next page, we're now going to learn how to use this unit circle a little bit. So what I'm going to do is I've displayed a couple of unit circles on here, and we're going to learn how we get these values now. So we're going to look at a unit circle and going to look at the sine of 5 pi over 3. So let's start with the sine of 5 pi over 3. So what you do on a unit circle is you just look at the y value. You don't have to look at y over r anymore because we know r is 1 in a unit circle. So if you go to your unit circle and if you locate 5 pi over 3, then we're really looking at this point right here. So what we're looking for is we're looking for the y value of this point. So that means the sine of 5 pi over 3 is going to take on the value of square root of 3 over 2. So that's all you really look at. If I want you to find a sine of an angle on a unit circle, you look at the y value. So if you kind of look, here's another example. If I wanted you to find the sine of 180 degrees, well, the answer would be 0. If I want you to find the sine of 2 pi over 3, the answer is 3 pi over 2. So what you're doing is you're simply looking for the y value. Okay, now if you want to go down and look at the secant by definition is going to be 1 over x. And remember, in a unit circle, the cosine of alpha is just going to be the x value. So what we need to do is we need to locate that angle 3 pi over 4, and then we need to look at this point, and it turns out that the cosine of this would just be the x value. So if I look at the cosine of 3 pi over 4, that answer would be negative square root of 2 over 2. Okay, you're in quadrant 2, and we learned that the cosine is always negative in quadrant 2. So that means that the secant is just going to be the reciprocal of that. So we're going to turn that upside down, get 2 radical 2, and of course we have a negative. Now we need to rationalize the denominator as we've been doing. So I'm going to multiply by square root of 2 over square root of 2. And notice what that's going to do is get me negative 2 root 2 over 2. 2's cross out, so that means the answer to this problem would be negative square root of 2. So when you're doing a secant on a unit circle, you're finding the cosine. The cosine's the x value, and then you just take the reciprocal of it. So that's how you're going to do that then. Okay? All right. Now, if we were going to look at a few things, other trig functions, we would basically do about the same thing. Just pull out the different definitions and then work them out. All right, so let's move on and let's look at the cotangent, and then let's do a cosine to finish this up. Okay, so if we're looking at the cotangent of 3 pi over 4, well, the definition of the cotangent is x over y, so we just need to locate, again, that point 3 pi over 4, and then we find x and y based on that point. So what we would have is, if we're doing x over y, we're really doing the x value, which is negative square root of 2 over 2, divided by the y value, which is square root of 2 over 2. Well, you can see pretty easily, I think, that that's negative 1. Okay, because you're taking the same number by itself. I guess if you didn't see that, well, how do you divide fractions? You multiplied by the reciprocal. Okay, so that would give negative 2 root 2 over 2 root 2. Everything cancels out, leaving you negative 1. So that's how you would do that. Okay. Now, let's say that we want to find the cosine of negative 5 pi over 4. Now, there's a couple of ways you could do this. One thing that you could do is you could convert this to degrees if you wanted to. So we know pi is 180 degrees, so 180 over 4 is 45. Then if we multiplied that out, we would get negative 225 degrees. Okay. So if you counted this out, it would go like this. This is negative 90, that's negative 180. Then negative 225 would actually take you to that 0.3 pi over 4. Another way you could do this, I like to teach students, is, hey, negative pi over 4 is negative 45 degrees. So just count to 5, okay? Go like this. I count, that's negative 1 pi over 4. This is negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, so that's negative 5 pi over 4. So where we end up then is we're looking at the x value. So what we're looking at is, since we're finding a cosine, we're simply looking at that x value. So that would give us the answer to this problem would be that the cosine is negative square root of 2 over 2. Again, the cosine is the x value. Okay? So that's how that goes. All right, so what I'm going to do is I'm going to scroll down a little bit, and then I'm going to have you all work out problems 7, 8, and 9, if you would. So what I'm going to have you do, typically when I do this, is I'll pause this. And what you can do is you can pause the video recording now and play back, and then I'll go over. All right, so let's resume this and let's see what you came up with. So first of all, in a unit circle, the sine is nothing more than the y value. So you need to go around your unit circle and find where 5 pi over 6 is. So that's the same thing as 150 degrees. And then you just look for the y value, and then that would be the answer automatically. So there's nothing to that. Okay, that answer is going to be equal to 1/2. So the sine of 5 pi over 6 radians is going to be 1/2. Okay, next problem. We're looking at cosine of 5 pi over 3. So you need to find 5 pi over 3. The cosine is the x value. So let's just find the x value of that point. The x value of that point is 1/2. So that would mean the answer to this, the cosine of 5 pi over 3 radians, is also 1/2. So finding a sine and cosine is very simple. Okay, now if you want to find a tangent, okay, we need to figure out what y over x is, and we need to count this out. Now let's consider this way. If you're doing negative 3 pi over 4, you can convert it to degrees if you want to, but I like to get students to realize that negative 5 pi over 4 is 45 degrees. So just count it out. Okay? Every time you're halfway in the middle of a quadrant, you're at 45. So that would be negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4 would be right there. So that's where the point is that you need to look at. So when we do this now, the x value is negative square root of 2 over 2. Then we're going to divide, whoops, I need to do the y value like this. So I need to do y over x, y divided by x. So the y value is square root of 2 over 2. Divide by the x value, which is negative square root of 2 over 2. So the answer to that, of course, would be negative 1. Right? So the tangent of negative 3 pi over 4 is going to be negative 1. Now, one thing I like to remind students a little bit, you're learning the unit circle, but it's also not a bad idea when you're doing this to get your calculator out and just kind of remind yourself of what you're doing here. So I wanted to show this just for a minute here. So I'm going to get my calculator. It's a good idea to turn your calculator on first. Okay. Brad, come on. Pay attention. Get yourself in radian mode. Okay, so I want to basically just go down to radian mode. Get that to highlight. Okay, so I'll press enter to get that to highlight. Like that, and let's just kind of review what you're doing on this now. So if you were doing the sine of 5 pi over 6, I mean, you can put in sine 5 pi divided by 6 And the answer to that problem is going to be 0.5. So that matches up what we got with the 1/2. If I wanted to do cosine of 5 pi over 3, I hate moving this calculator all the time, 5 pi over 3, then I'd also get 0.5, and then if I did the tangent, and I have to do this like this, negative like this, negative 3 pi over 4, then that'll give me an answer of negative 1. I just realized that I made a mistake on that, and you guys maybe have been wondering about that. So here's my mistake. Partially as I can't see very good, at least that's the excuse I'm going to say, is that both of these things are negative. So you have a negative y value and a negative x value. So the answer is actually positive 1. So see, that's the benefit of checking your work on a calculator to make sure. So look very carefully. And the other thing we learned is the tangent's positive in quadrant 1. All right, so that's what you should have got. Now we're going to move on, and we're going to begin to look at some graphing now. So this is where it gets real exciting. All right, so we're going to go around the unit circle, and we're going to do the graph of y equals sine x. And I'm choosing these values because these are going to give you the real special values that we're going to be looking for. So what I'm going to do on this now, if we're graphing the sine, then what we're looking for is the y values. So I'm just going to focus on the y values of these quadrantal angles, and we're going to use these values to draw ourselves a sine graph. Okay? So to begin with, we started with 0. The sine of 0 is going to be 0 because it's the y value. The sine of pi over 2 is going to be 1. The sine of pi is going to be 0. The sine of 3 pi over 2 is going to be negative 1. Then the sine of 2 pi is one lap around the circle, so it's back to 0. Now, if you looked at negative 2 pi over, or negative 2 pi, okay, that just means, of course, that you're going clockwise. So if you went clockwise 2 pi units, you'd be back to a y value of 0. If you did negative 3 pi over 2, that would actually take you to this point. So that would be 1, and so forth. Negative pi is halfway around the circle clockwise, so that's 0. And then negative pi is the same thing as 3 pi over 2, so that's negative 1. So those are going to be what we call key points on the graph of the sine wave. So what we want to do is I've created a graph, and notice I have the x-axis written in radians. It's important you always use radians. And then the y-axis I've got going from negative 1 to 1 because that's going to be the limit that you're going to have on this graph. So let's plot our points. You got negative 2 pi 0, so I'll just put a point there. Negative 3 pi over 2, 1. Negative pi 0. Negative pi negative 1. 0, 0. Pi over 2, 1. Pi 0. 3 pi over 2, negative 1. And then back to 2 pi like that. Now, you're going to graph this. Now, don't graph this way. A lot of times I see students, they want to draw it like that. That always reminds me of Charlie Brown's shirt. So the graph is not Charlie Brown's shirt. It's more curved. So it goes like this. So you're going to kind of graph everything, kind of connect everything in nice, smooth curves like this. That's not perfect, but you get the idea. So that's how the sine wave goes. All right. So as we go through on this, we're going to make a couple of key observations on this. The general shape of the wave that repeats infinitely is going to be this part right here. So I'm going to use my highlighter to explain what I'm talking about here. So if I was to go like this, that is considered one period of the graph, like this. In a sine, we usually have 5 key points that we talk about. Come on, stop this. I hate it when it doesn't do what I want it to do. There we go. Okay, so this is kind of what I want you guys to look at here, is In this graph, we have 5 key points. Come on, behave. Do what you're supposed to do. Okay, there we go. So the 5 key points are this point. That's the starting point. This is called the maximum. That's called the midpoint. That's called the minimum, and that's the ending point, like that. So that's 5 key points. So if you went from the distance, if you measured out the distance between those 2 points, that's 2 pi units. So the distance from an x value of 0 to an x value of 2 pi is 2 pi units. So the general shape that repeats is going to have a width of 2 pi, and we call this the period of the sine wave, like that. So you'll notice on this, if I was to go through and look at the other part of this I graphed, it's the same thing. So this part that I'm highlighting in green is just another period of the sine wave, like that. So that's the idea. Okay, so let's get a few other kind of key things about this. Generally, we call the graph of a sine wave a sinusoid, or a sinusoidal wave, a sinusoidal function. Since the shape repeats over and over again, we call it a periodic function. The reason that it repeats over and over again is all that's happening is the sine is a y value, and the angles are getting bigger and bigger on the unit circle, but they're coterminal to the angles we've already identified. So there is 5 key points. There are 5 key points in the cycle. They are I don't know why I put a blank there, the starting point, max point, minimum, midpoint, minimum, and ending point, like that. That's 1, 2, 3, 4, 5 key points, and it's going to repeat over and over again. All right, the domain is the set of all x values. We've certainly learned that. And in this case, the sign can be anything. So we would say negative infinity to infinity is the domain of the sign. And you can write that, if you want to, in set builder notation as set of x, such that x is an element of the real number system. If you're not familiar with this E is the Greek letter epsilon, and it really just says it's an element, or it's a member of the set of real numbers. So when you see this kind of funky looking R, that's the symbol mathematicians use for real numbers. Real numbers are any number that is on a number line: decimals, fractions, whole numbers, integers, everything. Okay? Just excludes imaginary numbers. All right, and the reason why the domain is all real numbers is if you look at this unit circle, the thing is, y is always defined. There's no point on the unit circle that does not have a y value. That's y. So if you look at the range now, what happens on the range is, the range we learned, of course, is the set of all y values in your function. So if you look at this, the lowest value in our table was -1, and the highest value was 1. So we would say the range of the sign is -1 to 1, or you could write that as set of y, such that then you would say -1 less than or equal to y, less than or equal to 1. So you're including -1 and 1. So a good way to look at this on the unit circle is, this is the biggest value y ever hits. That's the smallest value y ever hits. So that means that the y values range from -1 to 1. Well, these y values are changing. They're every kind of decimal value. Now remember, the unit circle only includes special angles, but theoretically there's an infinite number of y values on a unit circle. Okay, so that's how that would go. All right, let's go to the next page. We're going to do the same thing, and now what we're going to do is work on a cosine graph. And the way a cosine graph looks now is, in a cosine, we're looking for the x value now. So I'm going to go around the unit circle at the quadrantal angles and just highlight all the x values. And notice the x values are just kind of about the same as they were on the sine, although they're going to be at different locations. So let's go ahead and let's identify those. So starting with 0 radians, cosine of 0 is going to be 1. At pi over 2 radians, the cosine is going to be 0. At pi, you're going to have -1. 3 pi over 2, you're going to have 0. And then at 2 pi, you're going to be back to 1, like that. And by the same logic, if you filled out the values at -2, you would have -2 pi, you'd have 1. At -3 pi over 2, you'd have 0. Negative pi, you would have -1. And at negative pi over 2, you would have 0. Okay, just by looking at those values. So what we're going to do now is we're going to go ahead and we're going to plot those points. And as we plot those points, this will give us the value of the cosine. So we're going to start at -2 pi, 1. So it's going to be a dot. -3 pi over 2, 0. That's an x-intercept. Negative pi, -1. That's a minimum. Negative pi, 0. And then 0, 1. Pi over 2, 0. Pi, -1. 3 pi, 0, 1 like that. Okay, again, don't make a Charlie Brown graph. Make it nice and smooth graphs like that. Very smooth, continuous functions kind of like that. So graph it kind of like this, going carefully through all those points like that. So that is what a graph of a cosine wave looks like. Okay? Now, the period works like this. You're going to find that if we started at this point here and drew through that wave like that, that would be a complete cycle of that graph. A second cycle of that graph would be here, and I'll highlight this in green. So what we graphed is 2 periods or 2 cycles of that wave like this. In a cosine, it also has 5 key points, and the 5 key points can think of this as the maximum, the midpoint, the minimum, another midpoint, and then back to the maximum like that. So that's how that goes. So the width of that shape again is 2 pi. So the distance from 0 to 2 pi is 2 pi. So we'd say the general shape that repeats has a width of 2 pi. And again, that's called the period. Domain is all real numbers. Okay, so we can write it that way, or we could write it as set of x, such that x is a real number. The range is the set of all y values. So just like the sine, the lowest value is -1, highest value is 1. So we say set of y, such that y, and we write it like this actually. Let me erase what I just did there. So what we need to do is just write this like this. All right, as -1, you want to write this as -1 is less than or equal to y is less than or equal to 1. And again, if you look at this, see, this is the lowest point of x is -1, the highest value is -1. So that range, the y values are going from -1 to 1. Okay, so that's what the graph of a cosine looks like. Another thing I want to look at is just kind of some transformations for a few minutes and take a look at that. So as we're going through the next thing, let's say that we have a point 0,2, and let's say that we're shifting at pi over 2 to the right. This is stuff that a lot of times you learn in college algebra. So if you're shifting something to the right, what you're really doing is you're just adding to the x value. This problem you could even do in your head. So what you're doing is just taking that point 0,2, and what you're going to do is you're going to add on that x value. So we're just going to add on pi over 2, or I'm sorry, pi over 4, and then that's going to give you the adjusted or transformed point. Okay, so what we're going to end up having is the result of this point is just going to be pi over 4 and 2. Okay, so if we shift the x value 0 over pi over 4, we're just making it get bigger. Okay, same problem works about the same way. We have pi over 3 and -9 is the point. We're going to take this now pi over 3 units to the left. So if we're taking this pi over 2 units to the left now, what we're going to do is we're going to subtract that value like this. So we're going to subtract pi over 3 from the x value. So that gives you a new point, 0, -9. Now you can do that in your head, of course, but that would give you the idea. Okay, so here goes this thing messing up again. So let's go ahead and get this finished up. So what we're going to have is that would be our new point, would be 0, -9. All right, so if you're moving something to the right, add to the x value. If you're moving something to the left, subtract from the x value. Okay, so let's load up this next page here, and I will let you guys just very quickly work 14 and 15 out. I've given you a point, I've told you what transformation, and then let's see what we come. All right, so let's take a look at what you should have came up with here. Basically, you've got the point, pi over 4 and 2. So if you're going to move this pi over 2 to the right, that just means you add to the x value. That's it. Okay, so that's going to give 2 pi over 4, 2. Then if you reduce that fraction, of course 2 over 4 is the same thing as a half. So that's going to give pi over 2, comma 2. So that new point that you should have came up with is pi over 2, 2. Okay? Next point, I gave you pi, -5. So there's two transformations that I gave you. So this time I said pi over 6 to the right. So that means you need to add pi over 6 to the x value. I also said that you go 9 units upwards. So if you're going 9 up, that means the 9 would add to the y value. So I'm hoping you figured that out okay. Okay, well, we could get a common denominator of 6, so that we're going to just change pi to 6 pi over 6, add pi over 6, and then we're going to do -5 plus 9 to get the answer. So the final transformation would be 7 pi over 6, and then 4. Okay, so that is your solution, 7 pi over 6, comma 4 is your new point. If you make something get bigger to the right, you add to the x value. If you make something get bigger in the y value, you add. Very simple stuff to do. All right, next thing I wanted to talk a little bit about is the midpoint formula. So if you were going to find the midpoint, and let me just give you a real simple illustration of this, just a real simple idea. So if you had like the point 1, 1, and then say you had the point 3, 3. Like this. If you wanted to find the midpoint of these two things, what you really end up doing is you just end up averaging those coordinates. So what you would do is, if you take the x values, 1 and 3, the way you average two numbers is you add them up and divide by 2. Okay, so if you did that, that would give 4 over 2, so that would give a midpoint of an x value of 2. If you want to find the y value, then again you would just average up the y value, so you'd do 1 plus 3 over 2, which again is 4 over 2, so that's going to be 2. So this, what you're doing is averaging those coordinates, so you can tell by looking that that's going to be 2, 2. Okay? So think of your formula this way. You don't have to memorize the formula. If you're finding a midpoint between two numbers, you're averaging two numbers, so you add them up and divide by 2. So it turns out in graphing, sometimes we need to find a midpoint. So what we're going to do in these problems, we're not going to graph this or anything. If we want to find the midpoint of these 2 points, well, first of all, we would average the x values. So we add those two things up and divide by 2. Then we would average the y values, which is 6 and 8. So the average of 6 and 8 is 7. It's just the number halfway in the middle. So if we do this, we'd have 10 pi over 2. Then we'd have 14 over 2. Right? So that would give an answer of 10 over 2 is 5. So that's 5 pi. 14 over 2 is 7. So that would be the midpoint between those 2 points on a graph. Okay? So I will have you all work out 17 real quickly, then we'll move on and talk about the amplitude. So let's see what we got here. So again, we're going to just average the x's. The x's are -2 pi and 6 pi. So add them up and divide by 2. Average the y values, add them up and divide by 2. So what you should have got is 4 pi over 2 and 0 over 2. So the answer you should have got was a midpoint of 2 pi, comma 0. And that's it. So you'll be needing to do some midpoints sometimes when you do graphing. All right, the next thing I want to talk about on this page is what we mean by the amplitude of a sine and cosine. So the amplitude is defined to be 1/2 the distance between the maximum y and the minimum y value. So we're taking a half anytime that you find a distance between two numbers. And what's important about this, like if I wanted you to find the distance between 2 and 5, there's two ways to do it. You could either go 5 minus 2 and get 3, or you could do 2 minus 5, which is -3. But since distance is positive, that's the reason why we have that absolute value in the formula. So we're going to take a half times the y value of the maximum minus the y value of the minimum, and that'll give you what's called the amplitude of the function. All right, so moving to the next page. And this will give you a few ideas here. So if you are looking at a sine wave, this is a sine wave, so you have basically a maximum on this. This maximum is y equals 1. This minimum is y equals -1. So if you wanted to find the amplitude, you take 1/2 the distance between the max and the min. So notice what I'm doing is I'm just subtracting those two numbers. So that gives 1/2 times 1 plus 1. That gives 1/2 times 2, or 1/2 of 2 is going to be equal to 1. So that means the maximum value is 1, minimum's -1, the amplitude is 1. And again, what you're doing is on an amplitude is you're looking at half the distance between the crests of the waves. So that's something that's pretty easy to do in your head, is that distance between -1 and 1 is 2, but half of that distance is 1. So the cosine works out basically the same way. The minimum value of the cosine and the maximum value are the same. So the maximum is y equals 1. The minimum value is -1. So that means if you did the same formula, you're going to get the same thing as you did on the last one. So again, on a cosine, the amplitude is 1/2 of this distance. That distance is 2, but half of 2 is 1. Now, if you're looking at equations, the next thing we'll kind of look at is if you have y equals a sine x or y equals a cosine x, then the amplitude turns out to just be that number in front of the sine or cosine. So we say the amplitude is the absolute value of a. And again, the reason why it's absolute value is because amplitude is a distance, and distances are always positive numbers. So that's why. All right, so if you had these two examples, very simple on this. The amplitude is the absolute value of that number in front, so that would be 3. And then on this one, the amplitude is the absolute value of 7, so that amplitude would be 7. And what we're going to find is that amplitude changes the max and min of your graph. So the idea is if you had y equals 7 times cosine of x, what this 7 does is it multiplies all of the y values by 7. Okay, so that's going to really kind of do what we call a vertical stretch and a vertical shrink when you're changing that amplitude. All right, let's go next page. Now we're going to go ahead and do a couple of graphs here on this next page. So I've put a couple of unit circles on here so that we can look at this. So we're now doing the graph of y equals 4 sine x. So if we're doing a sine on a unit circle, we are interested in the y values. So we're only going to look at these quadrantal values for now, and we're going to get those things put together. All right, so let's go ahead and let's fill out our chart just for y equals sine of x, like this, okay? So as we're doing this, the sine of 0 we learned is 0. The sine of pi over 2 is 1. The sine of pi is 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is 1, and so forth. And what you'll find on this is these values kind of repeat themselves. So 0 and -2 pi are coterminal angles, so that's also 0. Pi over 2 and 3 pi over 2, -3 pi over 2 are also coterminal, so they will have the same value. Pi and -pi are coterminal angles, so they're the same, and pi over 2 and -pi over 2 and 3 pi over 2 are the same, so they have that. So again, you got your 5 key points. So what we're going to go ahead and do is, let's go ahead and get our graph put together. So you need to label these x values in radians, and you don't be lazy about this. You want to do this. Students a lot of times don't want to take the time to label everything. I always tell students, if you don't label your x and y axis, then you're not doing math, you're doing art. And kind of boring art too, that isn't going to win any contests in an art gallery. So take the time to do this. Now, one of the things you're going to find on this is the number in front is going to give that amplitude. So the amplitude is going to be 4. So what we're going to do is let's go ahead and graph this out. And we need to make this y-axis actually go all the way up to 4 because of that change in amplitude. And we need to make it go down to -4 as well. So what I'm going to do is I'm going to graph this, just pick a color and graph this like in green. So I'm going to plot all these points that we have here. So we got 0, 0, and just go ahead with me and plot these points and just kind of lightly dash these things in like this. And let's go through a couple of periods on this and get that established and labeled. So this is the graph of what I just drew in dashed lines, was the graph of y equals sine x. Now, what I'm wanting you guys to really understand is how the arithmetic works on this. Okay, what's important on this to understand is if you have y equals 4 times the sine of x, what that 4 does is it multiplies every y value by 4. Okay, so we're going to just start here, and we can do this in our head. There's nothing to this. So if we take the y value, multiply it by 4, we're still going to get 0 there. Go to the next thing in your table. Take 4 times 1. That's 4. And so forth. 4 times 0 is 0. 4 times -1 is -4. Okay, like that. All right, so what we have is that. Now you're going to see the same pattern on this, so I'll just kind of do this in your head. 0 times 4 is 0. 1 times 4 is 4. 0 times 4 is 0. 4 times -1 is -4. And then 1 times 4 is 4. So those are going to give key points. So I want you to understand that what's happening is the y values really get stretched. The graph gets stretched because the y values are multiplied by 4. Okay. Now let's draw the final graph. I'll draw this in blue, I guess. So I'm going to plot my points. So we have a point -2 pi 0. We have a point -3 pi over 2 4. I don't know why it does that. Pi 0, -pi over 2, -4, and so forth like that. So just go through and plot your points. And I think you'll see how everything works out. Now we're going to do kind of the nice smooth curves going through those points. This is so hard to do on this tablet. So that would be what your graph looks like, is like that. Okay? So that would be an example of the graph of y equals 4 sine x. Really what that does is doing an amplitude change is akin to doing a vertical stretch if this number in front of the sine is larger than 1. If it's larger than 1, it stretches it. Okay? Okay, so let's go down, and I'm going to let you all try the next one. Okay, so I'm going to move this down a little bit. You can pause this playback anytime you want to if you're having trouble keeping up. So let's go ahead and let you all work on this and see what you get. All right, so let's see how we did here. Now, what we're doing is a cosine graph. So I'm going to start by going around the unit circle, and we're going to look at the x values only. On a unit circle, we're interested in just x values. So we're going to create a chart on this. All right, so we're going to go around the unit circle. Let's start at 0. When theta is 0, the angle 0 radians, you have a cosine of 1, that's equal to 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is back to 1 like that. And then these points are the same. See, 0 and negative 2 pi are coterminal, so they're the same cosine. Pi over 2 and negative 3 pi over 2 are coterminal, so they are the same. And then pi and negative pi are coterminal, so that's negative 1. And then 3 pi over 2 and pi over 2 are coterminal, so that's 0. So the points are going 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So what you should have done was went ahead and plotted these things out. And what we're going to do is do this in a dashed line, and I'll see if you guys caught everything I wanted you to catch on this. So you want to take the time, of course, to get these things put together. And if you look at your amplitude on this, remember amplitude is always a positive number. So the amplitude is equal to 2. Now it's not negative 2 because it's a distance. So correct yourself if you made that mistake. So that's going to mean your y-axis actually needs to stretch up to 2 and down to negative 2 to fit everything in it. Now I'm going to go ahead and I'm going to plot like the original, just in like green. So I'm going to plot all this data that I have on my table of values, and then this is going to be just the basic cosine wave, which is a very simple thing to do. Once you catch on to it, you can draw these cosine and sine waves like real fast because they have this predictable pattern to it, like this. Okay, so that is going to be the graph that you should have drawn of y equals cosine of x. Just do that in dashed lines like this. Now, as you're going through and getting this graph, the thing that I want you to understand on here is, again, the math and the way it works. So if you have y equals negative 2 cosine x, again, what that does is that negative 2 multiplies all of the y values by negative 2. So that's going to actually cause two things to happen on this graph. You're going to stretch and you're going to reflect. So we're going to start here in this table, take the y value and multiply it by negative 2. So if you do that, you get negative 2. So what happens at this point is it really stretches, but then it reflects. So that's where that new point goes. The next point, you have a y value of 0. So negative 2 times 0 is 0. So you have a point negative 3 pi over 2, 0. So that's not really affected by that negative 2. Then the next point, take the y value of negative 1 and multiply that by negative 2. That gives positive 2. So it means this point actually stretched, but then it reflected like that. So you have that. So if you kind of look at your graph so far, you've got this kind of thing, right? Now, the rest of the points go like this, okay? You can just sort of fill them in. We've already done them all. That's going to be 0. That's going to be negative 2, 0, 2, 0, negative 2. So if you plotted these points, you would have negative pi over 2, 0. You would have 0, negative 2, pi over 2, 0, pi 2, 3 pi over 2, 0, 2 pi, negative 2. So the final graph that you should have came up with through 2 periods would look like that. Okay? So you have a reflection and you have a stretch. You have an amplitude of 2. Again, want to stress on here one more time that what the amplitude really is doing is it's finding half of that distance between those two values. Okay, so if you look at this distance right here, the distance from 2 and negative 2 is 4, but half of 4 is 2. That's why the amplitude's 2. So it's half that distance from the max to the min. Okay, let's push on. So hopefully you did well with that problem. So now, I'm going to finish up here with just a few things, kind of review a few things about amplitude now. So if you're given an equation, you want to know what the amplitude is. The amplitude is always the number in front of the trig function on the sine or cosine. So technically that's absolute value of 1, so that's 1. The next problem, the amplitude would be absolute value of 5, so that's 5. And then the next one, it would be absolute value of negative 5, so again that's 5. So that would be the amplitude, and that's how everything would get affected. The max and mins change as a result. So the number a that's directly in front of a sine, a cosine, multiplies each y value by a. Now these are mistakes right here. You want to be kind of careful about this. You never say just sine. That should say sine alpha, and that should say cosine alpha. I always tell students, this is kind of a stupid joke, that if you just put sine without alpha, then you are sinning. Okay, that is a sin to do that. So don't you do none of that sinning now, okay? All right, so put those angles on there, all right? All right, now we're going to look a little bit next at phase shift. And phase shift is now when we move things to the left or to the right. So we're going to kind of change this a little bit and look at a few graphs that look like this now. Okay, so A is the amplitude, and then this number B is going to be a phase shift. Okay, if you have X minus B, that's a phase shift to the right, so it moves that graph to the right. If it's plus, that takes that graph to the left. And then D is a vertical translation. So if you have plus D, you're going to go up. If you have minus D, you're going to go down like that. So one thing I want to kind of remind you of here is in college algebra classes, generally students learn a lot about functions. So here's an example of something that you may have learned in college algebra. Okay, for instance, this is a parabola. This is a quadratic function. So you learned, the graph of a quadratic, y equals x squared. And then you probably learned transformation. So if you're adding to x, that actually moves that to the left 3. Well, that's what we're doing with a phase shift, is we're just moving left and right. You also would have learned that if you're adding outside of that function, what that does is that takes you up 4 because the y values get bigger. And then what this is doing is, since you're multiplying y by negative 2, really, you're making the y values bigger. So what you're doing is you're doing a vertical stretch, and that negative right there makes the y's go to opposite. So you're doing a reflection over the x-axis. So what we're learning with trigonometric functions is the same as any function. They're all done the same way. So one of the things I like students to kind of get used to on a trig function, or just any function. I mean, if you just have a function f of x, and let's just say that we have a couple of numbers like here, all right, this is what happens. This right here is a left-right thing. This thing right here, that k, is an up-down thing. And then that a is really just kind of a stretch-shrink thing. Okay, so these all work the same way. Okay, so let's look at 26. 26, first of all, the amplitude is the number in front of the sine wave, so that's 1. The phase shift is the number in parentheses, so that's a phase shift of pi over 2 to the left, and it's to the left because of that plus sign. Generally, if you have a phase shift that's to the left, you want to put negative there. And then 27, the amplitude is the number in front of the cosine, which is 1. The phase shift is the number that's added or subtracted to x. So that's going to be pi over 2. And again, since that's a minus sign, that takes you to the right. That always is backwards of the way it seems to students, but that's the way that works out. Okay, so I'll just pause here just for a minute, and I'll let you all work on 28 and 29. And then as soon as you're done, you can press the play button and I'll see if you got everything right. Okay, so here's what you should have got on number 28. The amplitude is 2. The phase shift is pi over 4 to the right. On number 29, the amplitude is 2. The phase shift this time is pi over 4 to the left. And since it's going to the left, you want to use negative pi over 2 as the result. Okay, so let's move to the next page of the handout and let's begin to look at a few things with graphs. And as this loads up, we're going to talk a little bit about the range, and then we'll finish this section up with a few graphs. Okay, so the period of the sine and cosine is its width, and that's the width that repeats its shape like we said. So generally, if you have just y equals sine, and if you have like nothing in front of x, then that period is always going to be 2 pi. We're going to, in the next section, we're going to change that period. So if you put a number in front of x, like a 2 or something, then the period changes, but we're not quite there yet. So from this standpoint, everything in this section, the period's going to be 2 pi. Okay, so the period of this is 2 pi, period of the cosine wave, 2 pi. Okay, that's because there's nothing in front of x yet. Okay, the range is basically just it's always going to go like this on a sine and cosine. It's going to be minimum, maximum, and it's going to be a closed interval. So you're going to have brackets like this. So first of all, without graphing on number 31, the first thing that you want to look at is the amplitude is the absolute value of -5. So that's 5. So that number right there is changing the maximums and the minimums like this. So what's going to happen now is you're going to now have a minimum of -5, and you're going to have a maximum of +5 as a result. There is no vertical translation, so that's what you're going to have. The period's 2 pi, so the range is going to be on the closed interval from the minimum, -5, to the maximum, okay? And all that negative does is reflects it, but you're still going to have a minimum of -5 and a maximum of 5, okay? So the next one, the amplitude on this one is going to be absolute value of -1, so that's going to be 1. So what that means is if you just had the graph of negative cosine x, then we would say the range would be -1 to 1 as a result, because the max and min don't change. But since we have this number, that 5 is moving you up 5. So what's going to happen is we're going to move both of those values up 5. So that means the new range is going to be 4 to 6. So that would be the answer to that problem. That's what the range is from that value then. Okay. Now a couple of things I want to do as I'm thinking about this on here is if I was to go through and look at the amplitude, I want to use the range as just kind of as a check here. Remember, the amplitude is half the distance from the min to the max. The distance between -5 and 5 is 10. Half of 10 is 5. That's why that amplitude turned out to be 5. Okay, if you look at the next problem, the distance between 4 and 6, that in your head is 2. But half of 2 is 1. That's why that amplitude turned out to be 1. So that's kind of an important distinction and connection to make as you're doing this. All right, let's go to the next page. We're going to do some graphs now. All right, so I'm going to do a graph on number 33, And we're going to use this unit circle to kind of give us some key values on this. So we're going to do the graph of y equals 3 cosine of pi over 2. And we'll use the unit circle to assist us a little bit with a few things here. Okay, so let's first of all identify everything. Well, the period's 2 pi. Like I said, there's not a number in front of x, so you really have a 1x, that's the period. The amplitude is this number, so that's 3. The phase shift is this number, the pi over 2, and that's going to go to the left, so we're going to use negative pi over 2. Okay, in order for there to be a reflection, there would have to be like a negative 3, so there's no reflection over the x-axis. So when you're doing a graph with an amplitude change and a phase shift, well, the first thing you want to do is just go ahead and identify everything. And as we're doing this, let's go through and let's get our x-axis put together. So we're going to just use these same quadrantal angles, pi over 2, pi, 3 pi over 2, and 4 pi, or not 4 pi over 2 pi, sorry. Okay, so that's 2 pi, right? And then you want to go ahead and do the values, the negative values on the x-axis as well. So let's see, that goes to 2 pi. So do these backwards. So that's negative pi over 2. This is negative pi, negative 3 pi over 2, and negative 2 pi like that. Okay. Now, since you have an amplitude of 3, okay, that's going to pretty well tell you that, and you don't have a up-down transformation, so a logical way to scale this y-axis is to go up 3 and down to negative 3. So you want to be sure that you have your x and your y-axis scaled correctly, okay? So what we're going to do is we're going to start by just doing the graph. I'll do this in green, just the basic cosine. We're going to do the graph of cosine of x with no changes whatsoever to it. Okay? So now on the unit circle, again, if we're doing a cosine on a unit circle, we are just interested in x values. So I'm going to go around all of these quadrantal angles and just highlight all those x values. Okay? And then we're going to fill those out. We don't need to do a table of values anymore. That's really unnecessary. So if you begin to look at this, you would have at 0 radians, we're going to have a cosine takes on a value of 1. At pi over 2 radians, cosine 0. At pi radians, the cosine takes on a value of negative 1. 3 pi over 2, cosine 0. 2 pi, cosine's 1. And so forth. And like I said, the faster you get this memorized, the faster you can do these graphs like that. So I'm just going to go through, kind of follow the pattern, and get this basic cosine wave put together like this. Okay, so that'll take care of that. Now, what we're going to do is we're going to do this in 2 stages. So I'm going to take like a different color. Let's take like, say, blue. Okay? And let's do a second translation. Let's do y equals 3 cosine x. Now, all that's going to do, but before we do that, we got to do the phase shift. What you always want to do is, this is important too, is you want to start at the phase shift. Okay, you could actually do this problem in either order, but it's pretty important to develop the habit of just starting with the phase shift. So actually what I'm going to do instead is my second graph, let me erase this, is let's do instead the phase shift. And let's not worry too much about the 3 until the very end. So let's get this straightened out here. Okay, so let's do the graph of cosine of x plus pi over 2. Okay, so I'm going to actually start over here. Now this is a phase shift, pi over 2 units to the left. So it doesn't matter where we start really. Let's just start way over here. So let's take this point and let's move it to this point. So that phase shift's there. Take this point move it there. Take this point, move it there, and so forth. Okay, now once you kind of get that idea, then you can begin to just sort of cycle through those points now that you've got that established. Okay, so I'm just going to go through these points kind of one at a time, the ones that get phase shifted, and then we'll get that established, and then we got one more stage to finish up the problem. Okay, so we got everything done there. We've kind of gone through 2 cycles like this. Okay, so just kind of focus in on that blue graph. Now let's do one more in a darker color. Let's do like, actually I'll just do like black, and I'll do that in kind of a darker color. All right, so the final product now is going to be, our solid line is going to be y equals 3 cosine x plus pi over 2. Now all that's going to do is it's going to take all of these points on the blue graph, and it's going to multiply their y values by 3. So I'm going to go around and just kind of circle all these points on the blue graph, and all of these y values get multiplied by 3, so that's causing an amplitude change or a stretch. So this point's going to stay the same. This point right here, -1 times 3 goes down to -3. This point here stays the same. This point here stretches up to 3. This point here stays the same. So if you go through and now connect these dots into the nice curves, that's what one period of that graph would look like that then. And then just kind of go through the next things. This y value is -1, so -1 times 3 is -3. This point has a y value of 0, so it's not affected. This point moves up to 3, it gets stretched, and this point stays the same. So if you understand the mathematics behind what that 3 is doing to the y values, then you got it made. Okay, so that would be what that final graph looks like that. Now, as a student, you can do this all in one step. I'm trying to show you transformations. I have no problem whatsoever on graphs like this if you can just do everything in one step. And what you do is you just take the basic cosine wave, start at the phase shift, then do that amplitude change, and you can generally process that in your head pretty good. All right, next page. All right, I'm going to do one more. Then I'm going to put you to work on one just to kind of finish this up here. So this time, what we're going to be doing is a sine. And then we got a phase shift and we have an amplitude change on this. So since we're doing a sine, we're now focusing on the y values in the unit circle of these quadrantal angles. So let's begin by identifying whatever we need to identify here. Let's go ahead and get the x-axis put together, and again label it. So pi over 2 pi, you'll do this so many times that you'll get this memorized. 2 pi, let's see, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi like this. Now let's go through and let's identify everything. So the period comes from the number in front of x, okay? That's 2 pi. We're not ready to change the period yet. The amplitude comes from that number. So the amplitude's 1/2. Phase shift is pi, but that's going to go to the left, so that's negative pi to the left. And again, there is no reflection on this, okay? So no reflection. If there was, we would consider that as we go through. Okay, so let's go ahead and let's get all our data. Let's make the y value go up to 1, down to -1. Since we have an amplitude of 1/2, that means the max is going to be at 1/2, and the minimum is going to be at -1/2. So what we're going to do is we're going to go ahead and just go around the unit circle and plot these points. So you can look at the unit circle. We have a point 0, 0. We have a point pi over 2, 1. Pi, and I'm not doing the phase shift yet. What I'm graphing right now is just the basic y equals sine x. So we want to start there. Okay, so we have this 3 pi over 2 negative 1, 2 pi 0. And let's just do dashed lines to represent the very basic sine wave before we start translating it. Okay, then you can get the rest of the points real quickly and efficiently, like this. Okay, so that takes us through stage 1. Now, what we're going to do is we need to start at that phase shift. So this is a real important thing to look at, is let's look at our phase shift and let's create the second step of the graph by focusing on the phase shift. So the second step of this graph is to consider y equals sine of x plus pi. So let's just pick a point. Doesn't really matter where you start. Let's just start here. This needs to phase shift pi to the left. So this point right here goes all the way to there. So it phase shifts. This point right here moves over to this point. So if you look at this second point, this point here moves over to there. Okay, that takes care of that point. Okay, then if you look at this third point right here, it moves over there. So it's now been moved there. This point here phase shifts, so it moves there, and so forth. Now we can go ahead and start dashing this in right now. And the nice thing about the sine wave is once you get 2 or 3 points, you can tell where the rest of the points are going to go. So this point's ready to be at its max. That point's ready to be down at the x-intercept. So what we're doing on this is we're just kind of doing a phase shift on this. All these points get phase shifted. So just fill in the rest of the points. Like this, and then that'll give you the second stage. So what's happened is that graph in the red, just in your mind, imagine that thing moving. Just think of the red graph as moving pi units to the left. That's what happened to all those points. Okay? Now we're ready to do our final stage on this graph. So on this final stage, what we're going to do is now consider the amplitude. So the amplitude, when we put the whole thing together, we'll do this in a solid graph. So that is y equals 1/2 sine of x plus pi. Okay, and again, what this amplitude does is it's going to multiply all of the y values by 1/2. Okay, so let's start with any of these points on the green graph here. Let's start over here. If you take this point right here and multiply that by 1/2, the y value 0, 0 times 1/2 is still 1/2. That point's not affected. If you take this point, you're taking 1/2 times -1, so that goes up to this point. So you're doing like a kind of a vertical shrink. Okay, and again, once you get all these points, you're going to see how it goes. This point right here has a y value of 0. 0 times 1/2 is still 0. So that's unaffected. Okay, if you take this point, you're taking that y value of 1 times 1/2, that gives 1/2. So that goes like this. Now, once you kind of get this, then you can cycle through the points. You can predict where the rest of the points are going to go to get your final product like this. Okay, so that would be the official graph like that. We did that in 3 stages. So you've got the phase shift, and then you've got the amplitude change like that. Okay, so pause if you need to look over what I did on that. And again, you can do that in 1 stage if you want to. Okay, I'm going to have you all try number 35. Now, one thing that I want you all to do on this, I want you to make a change. So I want you to change this problem just slightly to y equals -3 sine x minus pi plus 4. Okay, so what I want to have on this is a period of 2 pi, an amplitude of 3. You're going to have a phase shift of pi to the right, And now this time you are going to have a reflection. I want to make sure that you guys can handle that okay. Then what I want to see is you also have this up 4 thing as well. So I'm going to go ahead and let you all work on that problem a little bit so you can go ahead and begin that. I'm going to go ahead and get the scale on this put together for you. And then you can go ahead and start working on it. And you can pause. I'll tell you when to pause. So I'm going to go ahead and let's get these values in the x-axis. And then think about how your y values go. Your y values on this got to go up to 7. Okay, so let's go like this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, negative 5, negative 7 like that. Okay, so now you're all set up. So go ahead and see if you can get the final graph. You can do it in multiple stages like I'm doing if you'd like to. Right, so I'm going to pause, let you work on it, and then that'll pretty well just about wrap us. Okay, so since we're doing a sine, again, what this means is on a unit circle, we're looking at y values. So I'm going to go ahead and in red, I'm going to very lightly graph out all of these, just basically the sine wave to begin with. Okay, so first thing I'm going to have 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi like that. So that's going to take us through one cycle. So you should have started kind of like that. And then you can back up and go through the other points. You want to make sure that you did these okay. You're getting this from the unit circle like we've been doing. Okay, so we're going to have that. So that's really stage 1 is you just graph out y equals sine x. Okay, stage 2 you want to work with the phase shift. So I'm going to go ahead and take this to green now. And let's do a graph of y equals sine of x minus pi. So that means you're going to take every point to the right pi. Doesn't matter where you start, I'm going to start with this point. This point phase shifts to the right pi, so that means it's going to end up there. So that's a point. That takes care of that point. This point here, phase shifts to there, so that takes care of that point. This point phase shifts here, so that takes care of that. This point phase shifts there, so that takes care of that. Now if you begin to go through and just kind of lightly sketch these points in, then you can easily get the rest, so you can follow the pattern on this for your phase shift. So we're going to focus just on starting with that phase shift like this. Okay, so stage 2 is done. Now, you can do the next stage all in one step if you want to, or you can do it in 2 steps. It doesn't really make any difference. I'm going to go through basically on this and try to show you how to do this in one stage. So I'm going to get the blue thing here, and I'll show you we're going to do the final product, and now what we're graphing is y equals negative 3 sine x minus pi plus 4. Okay, so here's what happens. Now I'm going to focus on all these points. I'm going to draw a little circle around all these key points on the graph that we just phase shifted. Okay, we hadn't done anything else. Now what happens is, this is really what happens in this problem. What you're going to do is that you're going to multiply y by negative 3. Then you're going to add 4. Now you're following order of operations, so you're multiplying, then you're adding. So let's start with this point right here. The point here has a y value of 0. You're going to multiply it by 3, then you're going to add 4. So the result of that's 4, so this point moves up to 4 like that. So that point is now, we're done. Okay, now we go to this next point. That has a y value of negative 1. So you're going to go negative 3 times negative 1 plus 4. Okay, like that. Well, that goes to 7. Okay, that's 3 plus 4. So this point moves all the way up to 7. That takes care of that. Okay, this point has a y value of 0, so it's going to match with this point. So it's going to have a y value of 4. This point right here has a y value of 1, so you're going to do negative 3 times 1 plus 4. Well, that's equal to 1. Okay, like that. So that point right there actually is going to have a y value of 1 when you do that. Okay, so that's moving down to that point right here. So what we're doing is looking at kind of at this green graph right here. And what's really happened on this point is it's stretched to 3, but then reflected to negative 3. But when you move it up 4, it just stays at this point right here. So that's where that point goes. So now I'm just going to kind of connect these as I go. So that goes like this. Okay, this point we've already done this. So we've done everything. That goes up to 4. Okay, so that takes care of that. This point has a y value of negative 1. We already did that. That goes to 7. So it takes care of that point. Okay, this point we've already done. That goes to 4. This point we already did. That stays at 1. This point right here stays or went up to 4. So what you should have had basically is this graph right here. So you have, the y values were 4 there, the y value was 7 there, and the y value was 1 there, like that. So that's what you should have come up with. So you can manage that whole thing in your head just by doing some arithmetic, and that's what I recommend. All right, so that would be it. I'm going to explain a couple things on the next page to finish this up. A little bit of a guitar demonstration on this now. So one thing that I wanted to explain on this is acoustics and sound waves. So like this is the note A on a guitar. That's my open A string. And it cycles at 440 cycles per second. It's called a standard A. There's different types of A's. There's like a Germanic A. Some bands will tune their guitar down a half step to a different type of A. But the standard is 440 cycles per second. And that's A. In music theory, an A major chord is made out of A, C sharp, and E. That's called the root, the third, and the fifth. So C sharp is this number. Here's a number. Tone. E is this tone. So you have... Those are the three notes that make up what we call a major triad. And one thing I want you to notice on this is as the pitch goes up, so here's A, now here's C sharp, the green graph, a little higher pitch, and here's E, a little higher pitch. One of the things you'll notice is as the pitch gets higher, it gets more frequent. So if I was to go way up here, get a real high level sound, then the waves are going like, kind of like that, real crazy, like they're very close together. So what I wanted to show you on this is if you added all of the y values, you can actually add these three graphs together, you would end up getting this graph. So this is what the graph of a major chord looks like. And this would be a major, what I'm playing is this. Okay, that's a major chord with composed of those three notes. Now I can add as many notes as I want to with that. That's another A. It's another A, which would have a slightly different sound wave to it. So one thing that's kind of interesting, to me at least, is that we know the mathematics behind sound. And it ends up being dealing with sound waves. And these are very idealized. In a studio, actually, you can graph any type of recording, and the graphs are a little more chaotic than these because every musical instrument has what we call different timbral qualities to it, which change the graph even more. But in the world of pure tones, this is the way it would work out. Okay, so you're really doing algebra of functions. Okay, so if you took college algebra and you thought, algebra of functions, big deal. F of x, g of x, h of x, so what? Well, this is a perfect example. You have three functions because you have three notes. So you have this new graph, which would be the graph of the pure tone of an A major chord. Okay, pretty fascinating. A couple other things that you might find interesting, and a lot of this stuff you can Google on the internet and you might learn a lot about this. One thing that we get a lot of times in synthesizers, okay, a lot of synthesizers will have this thing they call a square wave. And it's a very interesting sound. Then you can have like what's called a hexagonal wave. They have different sound characteristics. So the idea is what you're doing is rotating. If you rotate a circle, well, you end up getting a sine wave as long as the amount of time is consistent. If you're not changing the time with which that is rotating. Same thing with a square. If you end up rotating a square, then the sound waves tend to be more like that. If you rotate a hexagon, it looks like that. And those change the timbral characteristics of the sound wave. So mathematics is everywhere. It certainly is in sound waves quite a bit. One of the things that you'll learn about is a little bit later is amplitude does something to a sound. The period does something to the sound. Every little piece that we put into that trigonometric function changes that sound in some way. All right, that's the end of this. Hope you enjoyed the lesson for today and a little bit of real-world application there at the end. So let me know if you have questions. Hope you enjoyed the video.